Hi. This isn't going to be a super long talk. We're going to talk about AWS Instance Metadata Services. Who in the audience knows that their infrastructure makes use of that service? Okay, a couple of you. Everyone should know about it. And AWS should fix it, but we're not going to get into those details. We're going to go into how you can fix it yourself, because AWS is never going to. So let's start with my background. So my name is Peter Smith. I'm the founder and CEO of Edgewise Networks. Started the company with my co-founder, Harry Sverdlov, Chief Technology Officer of Carbon Black for 10 years, and the pioneer behind application whitelisting. Those details we'll talk a little bit at the end. Let's get into it. So we're going to talk about how you can exploit AWS Instance Metadata Services, some of the limitations of existing controls. So could you use IAM roles to minimize the effect of somebody getting into instance metadata? What about security groups, so on and so forth? And then we'll talk about why software identity is important for thwarting this sort of access and the repercussions. So we'll focus on technology that we have, but I'll share some thoughts on other approaches you could use, third-party software, open source software, to accomplish a similar outcome. So instance metadata. This is from AWS's documentation. And I know you can read, but I'll add some dramatic effect. So they put this big warning here, basically saying AWS Instance Metadata is a metadata service that allows you to collect information about an instance. It includes all sorts of information. And they say very clearly here, although you can only access instance metadata and user data from within the instance itself, that's pretty naive. The data is not protected by cryptographic methods. It is plain text HTTP. Anyone who can access the instance can view its metadata. Therefore, you should take suitable precautions to protect sensitive data, and don't store stuff in it that you wouldn't want people to see. So plain text, unauthenticated, but it's only visible from within the instance. So how do you access this thing? You've probably seen the address 169.254, 169.254, port 80. That's called a link local address. It's effectively a layer 2 broadcast domain specific address space that AWS took this specific address and they said any instance that goes out to the network to that address and port is going to see a reflection of metadata that's relevant to the instance asking for it. And it just gives it to you in plain text. So we're going to go into how exactly someone that you don't want to have access to it would access to it. And the one that's most recently in the news is the Capital One data breach. The way that happened was there was an SSRF where the attacker on the outside was able to pass in the URL to the instance metadata and put it in a path that said, get me security tokens. They grabbed the security tokens out and used them to connect to S3. So this idea in the AWS documentation that it's only accessible from within the instance is, I don't know why someone would write that. It's foolish. This is a nice hand drawing that somebody did on the internet for the sequence of attacks that occurred during the Capital One breach. But the TLDR here is that you've got the AWS instance metadata service at the hypervisor level. You've got the EC2 instance. The attacker comes in from the internet, drops a request into that exposed web application. In this case, it was actually a misconfigured WAF. And that was able to query the metadata services. So I know you guys are all security professionals, you know what an SSRF is, but I'm going to be pedantic and tell you anyway. An SSRF is a server-side request forgery. And the simplest way to think about it is it turns an application or a piece of code into a proxy. That's all it is. You pass in a URL parameter that itself contains a URL, and that software will go fetch the contents of the URL and pass it back to you indirectly. The SSRF makes another server act as an intermediary for you, the attacker. So let's actually look at what that looks like in real life. So SSRFs happen for a lot of reasons. Sometimes people misconfigure Nginx, they misconfigure mod proxy or whatever tool they might happen to be using. In the case of Capital One, it was a, I think it was actually mod security in Apache that was misconfigured, allowing it to behave like an SSRF. So what I've done is I've put together a bit of pseudocode. It's very readable, that does an SSRF. And this is probably one of the most common approaches for SSRFs happening in your environment is app developers that are, they think they're doing the right thing, but at the end of the day, they leave a gaping hole. A common example of that would be if you've got a web page that stitches together in iframes a bunch of different data from a bunch of different pages, the app developer will often make a mechanism where you go to a single URL and you pass in a bunch of arguments to get the other content, and they think this is benign, but in reality, they've just made an SSRF, and if they don't correctly filter out the parameters that can be passed in, they can be used for malicious purposes. So let's look at this right now. I'm going to switch to the podium. Hi. All right, so we're going to go to the bad server, which is red, and there's a green one, which is good, just so you know. And what we're going to look at here is, I have to log in first. This is a simple Flask app. And really, it's brain dead simple. What you've got here is ignore all the boilerplate above. You can start looking where it says app route /. And really what it's doing here is saying, if I don't receive a parameter, just post a simple response. This is my home page, my corner of the internet. But if you do get a parameter, go and fetch the data and respond to the user with this information. Now, a lot of app developers will believe that their parameters are somehow, magically hidden from anyone figuring them out. But, it turns out they tend to use fairly common conventions like URL equals or something like that. And that's exactly what we're doing here. So when we go over to a web page and we load this, actually I have to start the app first, so bear with me. Just quit out of here, and there we go. So if we load this page, you can see that it loads it correctly. It says, welcome to my home page. This is the default page. Now, if I were searching around just by passing random parameters that were common, URL equals, I might discover that if I went like this, URL equals Google, that the SSRF goes and fetches that data for me on my behalf. I can put anything I want into it. And this raises the question of, what could you do with this? Well, an SSRF doesn't care about what address space you're asking for. In this case, I asked for Google and Yahoo. But if I pass an internal address, it'll gleefully go fetch it. So that could have been the CRM system on the inside of your network. It could be instance metadata. So let's point this SSRF at instance metadata. If we go to 169.254, 169.254, which, by the way, is the most difficult address to type in the whole of IPv4 address space. What we see is this garbage. This is a set of time sequences for information that has been in metadata services over the past n days. And all we really care about is what's in latest. So if we go into latest, you can see there's metadata and user data. User data is actually anything that you want to put in there. It's user definable. So oftentimes you'll put bootstrapping scripts in there. So if you've got a base image that has absolutely no function, you'll actually load it into the profile of the user data, and then when the system comes online, you go to metadata services, go into the user data directory, and start executing it as a shell script. Well, if you're not sophisticated, using password vaults, so on and so forth, you might have embedded passwords in there. So this is really sensitive stuff, but let's look at what's in metadata. So if we go into metadata, this is a list of everything that you can access from the metadata services. There's a couple that are interesting. Generally speaking, you don't want the ability to enumerate things like security groups. Well, You can just by adding security groups to the end of the URL. Or the one that we're going to focus on today is identity credentials right here. So if we add this to the URL, you can see EC2, great. You can see security credentials. And you can see EC2 instance. Now, you're going to see these credentials, and you've got 5 minutes to hack this system because they do auto-rotate. So there it is. These are the security tokens for the instance itself. So is this really a bad thing, or am I just making a mountain out of a molehill? And the reality is this. Oftentimes, people will mount S3 buckets in the path structure of their Linux file systems. And typically, the way you do that is you grant access to the S3 bucket using the security tokens for the instance itself, because guess what? The instance has access to its own security tokens, and now it can mount an S3 bucket. Well, the fact of the matter is, pointing that SSRF at this directory gives you the security tokens. You can now copy and paste this, put it into your S3 client, and mount this S3 bucket on an attacker system. So you really, really got to be careful about this. So what are the techniques that you could use to mitigate this? Let's focus on IAM. Most certainly, you really got to be careful how you use identity credentials for S3 buckets that have sensitive data. I know it sounds appealing to use the host's identity credentials, but you should use a vault and use separate credentials for access to those objects. Basically, ignore that this thing exists. You really should, which doesn't mean you're out of the woods on protecting instance metadata. What about security groups? Well, this is going to be really surprising to most people. Security groups can do nothing here. Security groups cannot control access to instance metadata, full stop. But what if they could? Well, guess what? It wouldn't matter, because security groups are dumb firewalls. A firewall has no idea what the software is that made the connection. How would it distinguish a connection from curl by the attacker or a connection from that SSRF versus a legitimate administrative script? Simply put, it could not. So security groups wouldn't help you if they were available, and they are not available. So that brings us to firewalls. I sort of killed my punchline there. Firewalls, they have no idea what the software's identity is. And microsegmentation, very specific granular path-based firewall policies. Again, it's built on the wrong foundation of address, port, and protocol. It has no ability to distinguish one connection from another based on software identity. So what is the better approach? There's a lot of solutions that do this. Please don't take this as sort of a pitch for Edgewise. Identity is the answer. Application firewalls, as an example, would be an effective mitigation for AWS instance metadata. You could use Open Little Snitch. That's an application firewall. Windows has one built in. It's not very good, but it's there. You could also do something like using net filters with a user-specific designation for who's allowed to do access or not. So you could say only root is allowed to access the instance metadata, nobody else. There's a lot of operational considerations in doing that, which is why I think software identity and container identity are the right approach. Verifying the cryptographic identity of the software before allowing it to communicate with the instance metadata service so that you can say this specific Python script is allowed to access, but nothing else. And that's an effective mitigation. So let's look at that. And yeah, so what we do is we verify software identity on both sides of the connection, blah, blah, blah. Let's get into it. So if I'm an attacker and I can gain access to the system, what could I potentially do? Well, one of the things, if I didn't have an SSRF, but I did have remote command invocation, or I was an insider and I had administrative access, but I wanted to do this sort of stuff covertly, is abuse administrative tools. So just as I can use the SSRF to access instance metadata, there's no reason that I can't use curl to do the exact same thing. Oops, yeah, there it is. So what if I wanted to be a little bit more covert? I didn't want the history of my shell to reveal my actions. Maybe I could use Python. And this is a completely separate talk. We won't get into the details here, but Python is the PowerShell of the Unix world, right? It's pervasive. It's on every system by default. And it's incredibly powerful with its base libraries. So I could just as easily go in and say, give me a Python-based interactive shell and say import requests and spell it correctly. So with the requests loaded, I could just say print requests get and say HTTP and go 169.254, 169.254, and say get me the text version. Okay, there it is. So I've obfuscated from just using straight command line where you're probably logging all of that. I'm actually doing this inside the context of an interactive Python shell. So the question is, how do I mitigate these sorts of things? And I'm going to switch over to the identity-based protection and then enable it, and then we'll go back and see how we can try to undermine it or circumvent it. So what I'm going to do is log in here. And the first question you always have to ask is, what is connecting to AWS Instance Metadata Services? Makes sense, right? So we're going to take this object, and we're going to say, show me all of the outbound connections, and I want to know for unmanaged, and I want it for specifically the Instance Metadata Services. So we've got all of these connections. We're going to make it into a segment, a group of objects that should or should not be able to access that. I've actually already done it, so I'm not going to do it again. You can see that here, all AWS metadata clients will just verify it is what we say it is. This is a list of all of the software on all of the devices that access instance metadata services. So really all we need to do is say that no devices are allowed to talk to metadata services except for this list of approved software that should be able to interact with it. So the way we do that is fairly straightforward. What we're going to do is say all managed devices, and we'll go to our policy builder. This will just take 2 seconds. I'm going to say local unmanaged, say 169.254. I'm going to block that. And then for this guy, the allowed ones, I'm going to do the exact same thing, just in reverse. So I'm going to say this is approved. Great. So everything is blocked except the things that are approved. The things that are approved are the software that are allowed to interact with that service. So when I do that, you've got to give it a second to propagate and whatnot. Okay, so what you can see here is that initially, the error that we get is a permission denied on Python. I won't do any more typing. So what we're seeing is that by default, nothing is allowed to interact with metadata services. You can see the permission denied down at the bottom right-hand corner because Python itself is not in the list of approved software that's allowed to interact with metadata services. Now, there are some questions about could I circumvent this and what is allowed? So that was Python as an interactive shell, but I could actually say that there's a specific admin script which is in the list. When I run that, it is allowed. So the point is, when you select an identity-based solution, make sure, and there are solutions other than Edgewise that do this, make sure that it has sub-process level identification so that it can disambiguate one script running from another script versus the interactive Python command line. And the reason for that is you can't just say Python can't connect to metadata services. Half of your tools are probably written in Python. So you need to be able to selectively add or remove those things. Same goes for curl, right? I think I've done a curl on this. I'll just do it again. So permission denied on curl as well. But what about our SSRF? That's really the whole point of this talk, right? So we start our SSRF, we come back here, and keep in mind that Python, that policy had nothing to do with whether it could access the globally routable internet. So we come over here and we say yahoo.com. What does it do? There's yahoo.com. It works, no problem. But what about the SSRF? Going to the security credentials. There you go, permission denied. So identity is the key to making this work. With an identity-based protection model, you can allow only what is necessary, apply the appropriate policy to let it do its function, to act as a proxy, to go fetch data from Google and Yahoo and whatnot, but stop it from accessing things that reveal your security tokens. It's absurd that you need to do this, but let me just say, you need to do this. So that really is the gist of it. I don't want to yammer on here. Any questions? That was fast. I'll get a mic for you.
So after the Capital One breach, AWS decided to have IMD SV2, Instant Metadata Service version 2, specifically designed to prevent against such vulnerabilities. So in instance metadata version 1, you can, if there is an SSRF vulnerability, you can use get request to pull instance metadata and as well as the credentials. Whereas instance metadata service version 2, released by AWS just after the Capital One breach, ensured that you cannot directly invoke these endpoints to get it because it uses session authentication. So do you have any thoughts on that?
So my response is that the other vendors have the same idea. Microsoft, Google, they all have instance metadata services. And their idea of protecting it was adding a header value to the request that says use equals metadata. That's their version of authorizing access. Instead of just letting a plain HTTP request go through, it now has to have a header. To me, that just does not cut it. Not to mention which, it's still plain text. It's great that you had this header that no one could ever figure out, but I definitely know how to snoop on the interface and get the data a different way, right? It's not rocket science. They shouldn't have these services the way they have them right now.
Other questions? Other questions?
Yeah, there's one over here.
Yeah, I'm just curious. I think this approach works really well when you can very fine-grained say these processes are allowed. But how does this help, or do you have any ideas on how this helps approach protecting the metadata service? Should you not have the new metadata service from AWS enabled when your application actually needs to talk to the metadata service? So your web application actually needs to interact with the AWS APIs, therefore should talk to the metadata.
Yeah, typically separate the concerns, right? If it has to do it, have it done in a separate process that's not directly listening on an interface that's behind a load balancer or, heaven forbid, directly connected to the internet, and use a side channel communication to talk to that service. Make it more of a microservice that intermediates the path of communication to the metadata service. It's not terribly complicated to make that happen, but the thing that is reachable from the outside world should have a minimal footprint in what it has access to directly. Anyone else? Awesome. It's break time.
Okay, thank you.